Hello everyone, and welcome to today's webinar, Smart Chart webinar series focused on SIMS. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted, however, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Charles McGee, Chief Scientist at EAG Laboratories, will be answering some of the questions during the presentation, and we will also collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce Tamel Buyuk-Limanli, Scientific Fellow and Vice President at EAG Laboratories.
Good morning, good afternoon, and good evening, wherever you are. Welcome to our webinar on dynamic SIMS. We'll start with a bit about myself. I have over 35 years of experience in surface analysis techniques, and the last 25 years have been focused on secondary IMS spectrometry. My journey with surface analysis has started during my PhD studies at material science in University of Florida. Since I joined EAG in 1994, I became a dedicated SIMS scientist and participated in the development of many SIMS methods. The most significant was P-core SIMS, which we will talk about during this webinar. There will be upcoming webinars showing examples of P-core SIMS in the next few months. So I recommend you join in if you want to see more of the application of this special technique. For the last few years, I have also been working in development of EAG's customer interfacing process to advise our clients which EAG services will help their analytical needs. In today's webinar, I will have a brief introduction to EAG, fundamentals of SIMS, and we will mostly be concentrating on several examples where SIMS is being used, such as ion-implanted silicon wafers, RF or laser compound semiconductors, mobile ion failure analysis in SiO2 dielectric films, glass surfaces, metallic film stack, and there is one surprise at the very end. We will conclude with strength and limitations of the SIMS technique. So a bit about EAG. EAG, as you can see from the map, is a global company with laboratories across 4 continents. The orange dots shows where the instrumentations are. The blue dots shows you contact offices. EAG has 600 highly educated employees and experienced scientists. We serve 4,000 clients per year who are located in 50 different countries. Our laboratories are at 20 different locations, with SIMS laboratories being in 6 places, one in California, the other one in Arizona, New Jersey, Netherlands, Shanghai, and Hsinchu, Taiwan. We receive the majority of the samples to be analyzed via delivery services. So a SIMS laboratory is around the corner from a UPS, a FedEx, or a US mail for you. This chart shows all the techniques available at EAG. We call it the SMART chart, which stands for Spectroscopy and Microscopy Analytical Resolution Tool. The vertical axis of this chart represents concentration detection limits in atoms per cubic centimeter or atom percent or parts per billion or trillion. Colors of each circles gives you what type of information is being obtained. The blue circles gives you elemental information, while the orange circles give you molecular information, as described in the legend of the bottom left corner. You can download this SMART chart from our web page and dive into it even further. The bottom axis is representing the analytical size range. So if you have a smaller feature, you will be looking for techniques that are capable of analyzing small features, or if you have a larger spot for better averages of concentrations, you would use one of the techniques towards the right hand. Dynamic SIMS occupies the center of this chart. As you can see, it has the highest dynamic range of concentration detection from atom percent level to parts per trillion level. And SIMS can measure all the elements in the periodic table, including hydrogen, which makes it a special technique. But there's one other benefit to dynamic SIMS, and it is the depth distribution measurement capability. In this chart, we're looking at different techniques that gives you in-depth information, and the techniques with an arrow points to a depth profiling. As you can see from SIMS, it has the capability of detecting few monolayer thickness films down to tens of micrometer depth. So SIMS not only gives you a high dynamic range of concentration detection, it also gives you a depth distribution from the very top of the surface to up to 40 micron depth. So let's talk about how the SIMS process works. This is a very simple schematic of a SIMS instrument. We have a primary ion beam source that is incident onto the sample, and it's rastered, and the particles are ejected from the sample, and these particles will be ionized or neutral. The ionized species are extracted into the mass spectrometer or mass filter, depending on the electric field applied. And by tuning the mass spectrometer to a specific mass, we send the signal into our detector. The signal that comes out of the detector is going to be either a mass spectra or a map of a specific mass. But most commonly, we receive a depth profile of a specific element or collection of elements or masses. And currently, globally, a dynamic SIMS technique is used in this mode more often than any other mode. There are three different spectrometers for a SIMS instrument: magnetic sector, quadrupole, time of flight, or TOF. Each one of them filters out the masses in a different way. Magnetic sector applies a magnetic field to filter out the desired mass through the mass spectrometer going into the detector, while quadrupole uses an oscillating electric field to filter out the mass that needed to be measured into the detector. Time of flight, on the other hand, uses the velocity or time of flight from the sample into the detector to differentiate between masses and filter them out. All three can be used for many different types of SIMS modes. I have to inform you that EAG 40 years ago started out with a SIMS instrument. As the Silicon Valley was growing in California, EAG felt the necessity of providing professional SIMS services. Since then, in the past 40 years, EAG has amassed 40 SIMS instruments globally, which includes all three types of these instruments, because each one of them has a strength and a weakness. To be able to do a complete SIMS analysis, you will need all three of them. So let's look at the different types of SIMS modes. There are roughly two methods where you use a constant continuous beam onto your sample that creates ejection of atoms from the sample of interest, and the sputter ions are detected as we described, and you obtain a depth profile. We call that the dynamic SIMS. Static SIMS, on the other hand, is a pulsed beam. So you send a pulsed ion that ejects species from the surface. It contains elemental and molecular information, and it only gives you an information of the top few monolayers. So this is the difference between the static SIMS and the dynamic SIMS. You can do dynamic SIMS or depth profiling using all three spectrometers, magnetic sector, particle, time of flight SIMS. But time of flight SIMS is mostly used for static SIMS for its capability of detecting molecular ions in high mass resolution. So the typical applications of dynamic SIMS are trace and matrix element profiling through the multi-layer structures. SIMS technique was initially developed for isotope analysis of geological samples for aging studies. But as I said, back when Silicon Valley was growing, semiconductor industry in the 60s necessitated SIMS analyses of dopants and impurities in these special semiconductor materials. And as these devices developed into a multi-compositional layer stacks, SIMS analysis became more complex to include dielectrics, metals, and multi-layer stacks, which opened the doors to be used for all solid materials like polymers and bulk ceramics. So this is another schematic of the dynamic SIMS process. We have a primary ion beam hitting a crystalline structure, and the secondary ions are being ejected, hence the name secondary ion mass spectrometry. The depth resolution, or being able to measure a width of a layer, is dependent on this mixing range. As the primary ion coming into your sample, the energy transfer creates a mixing zone, and the thickness of that mixing zone determines the depth resolution of the measurement. As you might remember from your physics days, elemental physics days, this is a momentum transfer. So the mixing is going to be dependent on the kinetic energy of the primary ions. So you can control the mixing range by controlling the kinetic energy of the primary ions or the angle of the primary ions. So we can basically vary these parameters to achieve the analytical requirements. But because the lower kinetic energy is going to give us higher detection limit or longer analytical time, we often end up analyzing samples in different ion beam conditions to be able to capture all the information that's necessary from a SIMS analysis. The depth axis in SIMS is calibrated in a very simple method. After the measurement, we do a stylus profilometer measurement of the sputtered crater, and then from that we calculate a sputter rate, and we convert the timestamp of each data point into a depth. We sometimes also use standard materials which has a known depth or thickness to calibrate the sputter rate as well. SIMS method has started by mostly analyzing ion implanted distributions in silicon material. The three most common dopants in silicon semiconductors were boron, phosphorus, and arsenic. Therefore, we have almost 40 years of experience in measuring these elements. We're looking at these three dopants, and as you can see, they have a variety of distribution shape, and the detection limits are in the E13 to E14 range. More importantly, we can, because it's a depth profiling technique, we can actually see differences in profile shapes. And in this case, we're looking at a phosphorus implant, and we are measuring the phosphorus implant at the edge of the wafer and at the center of the wafer. Even though the dose or the total amount of phosphorus put in the sample is the same between the center and edge, we see a big difference in the profile shape. This little hump in the profile is the channeling tail. So depending on the angle of the incidence of the implanting ion, you can channel it and end up having the ions go much deeper than in a different location. So SIMS is not only useful for getting a dose or total amount of implant concentration, but also these shapes gives you a clue as to how these are being implanted. SIMS is also used for tool matching or looking at how your instrument is processing ion implants over time. And this is a plot of 5 samples measured 3 times, and we're looking for 5 implantation of a silicon wafer at different times, producing the same dose, same shape, etc. When the overlay of 15 profiles in the slide and the dose calculations show that the relative standard deviation is about 0.17%. So usually in these types of studies, we're looking for less than 1% precision. As you can see, for the phosphorus and silicon measurement, SIMS does have the high precision to be able to provide that necessary information. Sometimes this method is being used for tools being installed at new fabs, and to be able to make sure that the 2 different tools are producing the same implant profile or dopant profile. We do this high precision implant characterization quite routinely. But as I said, as the semiconductor industry developed into a more complex layer structures, we started seeing binary structures. And one of the early on ones are silicon germanium on silicon back in the 80s to 90s. This is a silicon germanium HBT structure, silicon germanium being the base layer. In this particular profile, we're plotting the germanium concentration on the right-hand axis is atom percent. We're plotting carbon, boron, and oxygen. On the left-hand axis is atoms per cubic centimeter. And the goal here is to see where the boron dopant is with respect to the silicon germanium layer and carbon layers. What's the concentrations in the germanium and in the silicon cap layer, as well as looking for any possible contamination from oxygen during the epitaxial growth. This is obviously prepared using an epitaxial growth instead of ion implantation. In another case, we see that the similar structure silicon germanium sample has a lot of impurity layers, as evident from these oxygen spikes. By measuring the impurities, dopants, and the matrix elements at the same time, we can use SIMS as a guide to failure analysis. So if you notice, by comparing the oxygen spikes to the other elements being measured, we see that there's an oxygen spike at the epi-substrate interface. Then as the germane gas is being put on, we started getting an oxygen spike, or perhaps there was a growth interruption before the germane gas was turned on that put an oxygen spike here. Then as you stop the boron dopant or move on to the graded part of the silicon germanium, you put another oxygen spike that continued on into the silicon cap. All of these possibly could be a growth interruption and contamination that's coming from the chamber reactor chamber, or the change in temperature, growth temperature, is causing the incorporation of oxygen even higher. Nevertheless, SIMS, by detecting low-level impurities at different locations of a profile, can be used as a very good guide to do a failure analysis or epitaxial growth. Now let's get more complex and go into compound semiconductors. This is an indium phosphide HBT. We're plotting gallium to mark the indium gallium phosphide layers differentiated from indium phosphide layers. This structure has silicon dopant as an N-type dopant and the carbon as a P-type dopant. Because SIMS is the only technique to measure the dopant concentration and the layer thickness, one of the parameters we're looking to address in this analysis is the thickness of the dopant layers, which you cannot do, say, with microscopy at the same at these concentrations. We're also looking for impurities in the structure because we're putting N-type and P-type dopants, but we want them in the places where we want them to be. We can see that there is a carbon spike at the collector junction here, subcollector junction here, when we put, and it is maybe possibly due to a growth interruption. One thing that I want to point out here is that this gallium plot is plotted as row intensities to the right-hand axis as counts per second. And you would see some changes in the gallium intensity, but all these changes do not represent the change in gallium concentration. It's the way the signals come out of the SIMS instrumentation. When you see counts per second, you should be ignoring the changes in these intensities and use it only for marking the layers of, in this particular case, gallium, indium gallium phosphide. We can also look at other impurities in the structure like oxygen and hydrogen, since vast majority of the compound semiconductors are being deposited using metallo-organic compounds or gases. There are abundant carbon and hydrogen impurities. We can see that the growth interruption here put an oxygen spike here as well. We see a high hydrogen concentration under the carbon dope base layer, as well as the silicon emitter layers at top. So by monitoring the gallium and the location of these peaks, you can actually have a good failure analysis of where the epitaxial growth is having problems. One thing that makes SIMS analysis or providing concentrations tricky is it requires almost always a quantification standard. Plotting, as I mentioned before, plotting row intensities will be deceiving and leading to inaccurate assessment. To quantify a SIMS intensity, you need a standard, which is the known concentration of the element of interest in the same matrix as the sample being measured. The standard must be analyzed under the same analytical condition to determine the reliable calibration parameters. Most SIMS standards are generated by ion implantation into a variety of matrices, and expected accuracy in this case will be 15% or better. So just to show another example of where SIMS ion intensities are can be very deceiving, this is a plot of a boron implanted into silicon, and like every other silicon material, the surface has a native oxide of 2 to 3 nanometers thick, and we're looking at the row counts that comes out of the SIMS instrumentation. The point here is that the silicon intensity, as it approaches to the oxide, goes up by a factor of 10. But in reality, the SiO2 has only 1/3 of silicon in that SiO2 layer. It's 33% silicon, 67% oxygen. So why is the intensity going up? And the reason for that is what we call the matrix effects in SIMS. The ionization probability of the silicon ions in positive ions increases as the concentration of the oxygen in the material goes up. But the element of interest in this particular case is boron. So what is happening to the boron? How do we quantify the boron in such a shallow distribution when the matrix effects are changing the ion intensities in this manner? And the answer is you run an SiO2 standard and also a silicon standard to get to a profile shape that looks most reasonable. So this is the quantified profile of the boron. As you can see, it has the expected Gaussian shape, even though it's only 5 to 10 nanometer wide, and we see an oxygen marker for it. So it is possible by doing proper calibration to get to a profile shape that is reasonable in comparison to what comes out of the SIMS machine. So let's see how we can really do the conversion of ion intensities to concentrations of elements. SIMS quantification has a very simple formula. We calculated the relative sensitivity factor from a reference material and multiply that by the intensity of the analyte ion divided by the matrix ion, and that gives us the concentration of the element of interest at data point I. And the depth axis, as we discussed before, is determined by multiplying the sputter rate measured from a crater measurement times the time spent at data point I. Unfortunately, though, these parameters, the sputter rate and the relative sensitivity factors, change with respect to the change in composition. As we saw in the SiO2 silicon example, the relative sensitivity factor had to change from SiO2 to silicon for boron quantification to be done properly. This becomes a bigger issue to tackle with in compound semiconductors, because in compound semiconductors there are several layers at different concentrations. On top of that, the more intricate the compound semiconductors has become for photonics and RF devices, we found our customers requesting us to do these SIMS measurements where they can do better calibration of the dopants, looking for gradient abruptness, or looking for the location of dopant impurities in a greater accuracy than what we've shown in the indium phosphide HPT example. But also they were looking to get the matrix element quantified, because some of these elements are in very thin layers, like an etch stop, and they often has gradients, which makes it very difficult to be measured by the standard methods that they have in-house. On top of that, as these concentrations are graded and the dopants are put in these graded layers, one has to measure an accurate layer thickness. But the composition gradient will cause the change in sputter rate, so measuring the layer thickness is not as simple as applying a single sputter rate. All of this had led to a new method at EAG. We call it the PCOR SIMS, which stands for point-by-point correction of sputter rate and RSF changes at every data point with respect to the change in alloy composition at that data point. So how do we achieve that? For ionization calibration, we ion implant elements of interest into a variety of materials. We use some of the matrices to calibrate the ion dose that goes into these materials. We make an assumption that ion implantation into these different materials are exactly the same, and then study the ionization formation of these elements from one composition to the other composition, and develop a curve for calibration. To be able to do a proper, accurate calibration of compound semiconductors, you have to have the relevant reference material, relative standard. This is why EAG at this point have more than 6,000 standards to be able to do reliable SIMS characterization. So let's look at just the AlGaAs example in the previous slide. So we're looking at the RSF, or the sensitivity factor, calculated for carbon and silicon for a different AlGaAs samples varying in aluminum content. This is gallium arsenide, and this is aluminum arsenide. As you can see from this plot, that RSF from gallium arsenide to aluminum arsenide for carbon is changing by more than factor 3, or for silicon more than factor 2. So if you were to quantify carbon and silicon in a given AlGaAs sample and use either this RSF or that RSF, you'll be making almost a factor 2 error. But if you're armed with this kind of a curve, you can actually do a proper calibration using the percent aluminum. But this graph, application of this graph, requires that you measure the aluminum concentration in AlGaAs layers with some confidence. So here's a plot of a test structure, AlGaAs test structure. In this particular case, the customer wanted to measure the difference between two samples, sample 1 and sample 2, and just to make sure that this small difference, the 2 atom percent difference between the two samples is real. So the way we do that in SIMS is basically do a repeat of these structures, and when we do that, we find that the difference between the two samples are real because the standard deviation of the two measurements is less than 1% or less than 0.5%. In fact, you're actually reproducing these small variations in the AlGaAs structure. So for certain type of alloy compositions, SIMS can give you a very precise measurement of the compositions. And armed with a NIST certified reference for AlGaAs, you can actually be very accurate as well. But remember, SIMS measures the total number of elements in a total number of atoms in a matrix, in contrast to, say, an X-ray technique where it measures the total number of atoms at a substitutional site. So there could be differences between them because of that. So we have the curve, we have the AlGaAs composition methodology. Let's apply that knowledge to a VCSEL structure. We're looking at a PDBR layer of a VCSEL structure, vertical cavity surface emitting laser structure. And in this structure, from one DBR mirror into the other one, the AlGaAs composition is graded, as you can see. And the intention was to put a carbon dopant right at that graded AlGaAs interface. If we were to take the SIMS intensity and convert it into concentration using gallium arsenide RSF, we will get in this profile. But we know that the quantification requires multiple different RSFs because as the aluminum concentration changes. So when we apply the P-core SIMS, we find a carbon profiling in these structures closer to the reality with, and as you can see, at high concentrations of aluminum, the difference between using a regular SIMS with a single RSF versus P-core SIMS, the error could be as high as factor 2. Let's look at the VCSEL structure as a whole. This is a sample that has over 200 layers. It is 8 microns thick, and it has lots of different things going on in the device structure. This plot gives you an overall view of a gross contamination like oxygen at specific locations, dopant consistency in certain layers, in the PDBR or NDBRs, or any spurious contamination at the epitaxial interface, and also looking at a rough estimate of the composition variation. This is all good for a rough understanding of your VCSEL structure. However, in these devices, as we have seen in the previous example, there are layers that are only 10 nanometer wide, 10 to 20 nanometer wide. So to really understand what is going on here, you need to do a high depth resolution. Remember the kinetic energy of the primary ion beam to be able to get detection limits or the sensitivity of the very thin layers. And when we do that, we find these new features in these layers that we were not able to see in the previous slide. And this points out to a growth artifact in the epitaxial wafer. And this oscillation seems to be very periodic, and possibly because of the rotation of the wafer as being deposited. So again, by using a proper SIMS calibration, you can do a failure analysis of these intricate structures. One of the other very important layer in the VCSEL structure is the cavity region, or the active region with the quantum wells in the middle. It is very difficult to decipher the quantum wells in the structure, but by doing a high depth resolution through this layer, we can actually get a better understanding of it. Here we are looking at a SIMS plot and using P-core SIMS and higher depth resolution, and overlaying it to a electron microscope micrograph, just to make sure that the layer thicknesses in the P-core SIMS are properly calibrated, and it's matching the thicknesses as shown by the electron microscope. but we are actually looking for dopant in diffusion into quantum wells, and the dopant concentrations as the AlGaAs is varied. As we've been saying, P-core SIMS is needed if you want to measure a dopant concentration and a varying composition. And as you can see, you can do that very clearly in this analysis. We are resolving the quantum wells in this mode, but SIMS is never as good as a high-resolution TEM EDX analysis to really truly measure the peak concentrations of these quantum wells and do a study of it. And on top of that, if one needs to be looking at the interface sharpnesses, SIMS is not a good way to do it. You would have to do microscopy on top of doing SIMS. Because of that, SIMS and microscopy goes hand in hand in many of the, especially compound semiconductor analyses. So how do we get to that layer thickness accuracy that in contrast to the TEM measurement? Well, we have a plot of the sputter rate change from gallium arsenide to AlGaAs, and we plotted. We have this curve, and depending on where we are in the structure, what the aluminum concentration is, we know what ratio of sputter rate we need to apply. That leads to the correct layer thickness, as good as a microscopy we can provide. SIMS also has a very high depth resolution. It can detect single monolayers in a structure. This is an overlay of two samples, two SiON gate dielectrics. And the difference between the two is that sample one has the nitrogen at the oxide silicon interface. As you see, oxygen is going down, nitrogen going up, and then the silicon goes up after that. In sample two, the nitrogen is toward the surface and the oxide is growing underneath it. Each one of these are a single monolayer. So the total structure is roughly 45 monolayers. So with proper SIMS conditions, you can do studies like this, even if they are only single monolayer. So now that we have this method, we can apply it to other intricate structures like PHEMTs. Incidentally, I will be having another webinar next month on PHEMTs, gallium arsenide PHEMTs, and gallium nitride HEMTs. I will show one or two examples just to give you a teaser of what you are to see. This is a comparison of two PHEMT structures, and the customer in this particular case was looking for the reasons for a poor HEMT. The blue curve is having a low breakdown voltage. Because we have the high resolution, we can resolve these very thin delta doped silicon samples around the InGaAs channel region. And we see that in the poor PHEMT, the growth, the epitaxial growth spilled over the silicon into the Schottky layer, increasing its conductivity. So hence the breakdown voltage is being higher. I'm sorry, breakdown voltage being lower. This is the most recent transistor structures that are being used in electric conversion devices, a power transistor, a gallium nitride HEMT structure. It's grown on silicon for cost effectiveness, and it has three important zones. We have the AlGaN region that's grown to minimize the defects in the upper layers. Then we have a GaN layer that's doped with carbon. But one of the critical layer in the structure is this 2DAC, two-dimensional electron gas region. As you can see, while you're doing a profile of 4 microns in this material, you really cannot see what's going on in this layer. By now, you should know that SIMS, in a different mode, you can actually resolve monolayers. So let's look at that top layer and compare that top layer, which is only 30 nanometers thick, for carbon concentration, which is very difficult because you have a very high concentration of adventitious carbon on the surface that creates a tail into where you want to measure. But yet, in a proper SIMS sample prep and sample analysis, you can make a comparison between the two samples for as thin a film as 30 or 40 nanometers. And you can see that between the wafer edge and wafer center, There's a factor of 2 difference in carbon contamination. On top of that, for whatever the reason, the wafer edge has this carbon spike at the aluminum nitride AlGaN interface and right below the 2GaN region, which basically will be a killer. So these are all good semiconductor and conducting materials. Now let's look at some insulating materials. For us to be able to do proper SIMS analysis, we need to use low energy electron beam irradiating the vicinity of the analysis area to neutralize the charge buildup. However, depending on what type of electron beam you use, you may actually create more problems than you started with, especially in mobile ion analysis in SiO2 dielectrics. Here's an example. Lithium and sodium are known to be very difficult to measure by SIMS in insulating, especially in SiO2 materials. This is a lithium implant into an SiO2 film. This is the oxide silicon interface. And if you don't use the proper electron beam compensation condition, you end up with a lithium profile that drags on. But we know from theory and modeling that the implanted species have almost like a Gaussian shape with a very sharp drop if it's an amorphous material. So as you can see, what is expected versus what we get is grossly different. But with a little elbow grease and blood on the floor, you can actually get a SIMS profile that gives you a profile shape that is meaningful and what you would expect. So it is possible with little effort put in. Why is this useful? Well, here's a look at a BPSG, borophosphorus glass film that are used as dielectrics in CMOS structures. And you're looking at a device that has a mobile ion contamination, and the goal is to measure where this contamination source is. And we see that depending on how you do the charge compensation, you may get a very different profile shape, but the proper compensation shows you that you get a sodium spike at the end of the phosphorus source turnoff. So armed with this capability, we started to look at bulk insulators like glass. This is a pharmaceutical container glass vial. And recently there has been a lot of studies on understanding why the glass flakes form in these pharmaceutical solutions. And we use SIMS to really understand the surfaces of these glasses where the flakes are expected to be formed. And any variation of the surface concentration from the bulk composition would be expected to be prone to glass corrosion. So in this particular case, we're looking at different locations of the glass and looking at the cross section of the broken glass. We call it the fracture surface, and we compare the composition of each location with respect to the bulk composition. And we see that in the heel region, we have the biggest change in surface concentration with accumulation of sodium and boron and decrease in SiO2. If you look at it in aging with an acidic solution, we see hydrogen incorporation increasing as the days progress. And more importantly, what we're looking here is this as received unexposed glass surface have these higher boron and sodium concentrations, but after exposure to acidic solution, they all leach out, leaving a weak surface. Enriched with SiO2 looks like a sol-gel structure, and that basically flakes off into the solution. That's how you form the particles. We also look at low emissivity coating of window glasses. This has many layers, about 15. Each layer has a different function. We're asked to measure these 2 to 3 nanometer thick chromium layers around the silver. Also look at the changes between the annealing with respect to the as deposited. These 2 layers are put in, the zinc tin oxide and silicon nitride, to prevent sodium diffusion from the glass into the upper layers. But with the SIMS analysis, we can see that that was not possible. The sodium after annealing has diffused from the glass into different parts of the structure, but the other layers have remained intact. In a different sample, when we compare as deposited versus anneal, we find that the nickel actually had diffused out immensely between annealing. So it started out with a peak that ended up with a long tail. So having the high resolution analysis with matrix elements like this, you can do a SIMS analysis pretty accurately. One of the challenges that we have is profiling through a polycrystalline metallic film. In this particular case, we're looking for copper diffusion into the silicon. But when we're profiling, the copper roughens and it creates peaks and valleys. When we reach the silicon and we see a silicon signal, we also get a signal from the copper, which essentially does not represent the true copper concentration in the silicon. So in the SIMS profile, it looks like copper is diffusing into the silicon. But in reality, when you do the profiling from the backside, from the silicon side, by thinning the silicon layer into about a micron, we know we can create a very flat crater bottom. We can do a proper analysis, and we find that in reality, copper did not diffuse into the silicon. Titanium nitride created a very good diffusion barrier, and there was almost no copper in the titanium nitride either. So you have to think out of the box and look for solutions on how you can do analyses in complex structures like this. Now here's the surprise. So we can do lots of solids with SIMS. And sometimes when we're doing a lot of SIMS, we get really hungry and we open up a potato chip bag and start crunching onto those chips. And we think like, what, I wonder, keeps these potatoes so crisp and they'll go stale as soon as they are exposed to air. And we go in, the scientist in us makes us go and look at that bag from the surface into the bulk of the film, and we find that the reason this potato chip is very crisp is because there's a nitrogen containing layer in this bag that acts as a vapor barrier. So the strengths, as I was able to show you, it has the excellent detection sensitivity for dopants and impurities. It can detect all elements, including hydrogen, and measure composition in some of the applications. But the limitation is that it's a destructive technique. It requires very specific standards, and it gives you only elemental information, not chemical information. I'm going to skip this slide in the interest of time, just to tell you that SIMS, in combination with other techniques, gives you a very accurate assessment of your material, one of which is differential Hall effect measurement that EAG recently has acquired. It gives you the active dopant. Remember, in SIMS and semiconductors, you're measuring total elements. So you have no idea what percentage of these elements are actually activated. So you would need another technique like a Hall effect measurement that gives you a depth profile of the active dopants. We also use RBS and XBS to do matrix quantification and calibrate the SIMS intensities. For surface impurities, we combine it with TXRF. But as I said before, STEM EDS is one of the techniques that we use in combination with SIMS quite often. One little note, through the COVID crisis, EAG Laboratories has stayed open and still open and operational. We would highly encourage you to use EAG because confidentiality is the core to our business. We realize that we're doing intricately sensitive information and needed to be kept confidential, and we have all the systems in place to protect that. Because we have multidisciplinary approach due to multiple different techniques and 2,500 instruments worldwide, we are the global leader in independent materials testing services. The easiest way to get in contact with us and give us questions or help and request help is eag.com/contact.